Okay, so this is a space science class. This is the first formal lecture on space science. In last meeting, we've talked about an overview of what we're going to study this semester, which is the science of the space environment. And as you already realized, that most, or if not all of the topics that we're going to discuss are based uh, on the physics of space plasma. Okay, so today we're going to talk about one aspect of the science of space plasma, which wherein we're going to talk about the motion of a single particle in an electric and magnetic field, no? Because the plasma that we're talking about when we study the science of space environments is, I don't know, is embedded in different forms of magnetic field. So you'll have your solar magnetic field at the surface of the sun, wherein most of the activities are based, solar activities are based from. And then the solar atmosphere, which is dominated by the solar wind, which carries the interplanetary magnetic field because of the fact that solar wind is a charged particle. And we know from our electromagnetism class that moving charges create or carry its own magnetic field. And also, the Earth that we want to study, it has its own magnetic field. And all this, I don't know, all these magnetic fields are related to each other, and they dictate how the charged particles in the space environment behave. Okay, so the outline of the lesson today are the following. So we will have some review of how electric and magnetic forces affect charged particles. And from that, we're going to study or talk about gyro motion as well as particle drift. So remember that gyro motion and particle drift are two distinct kinds of motion of charged particles under the influence of electric and magnetic fields. And from there, we're going to define the three motion invariants that, so these three motion invariants, so that means these are the three kinds of motion that a particle or a charged particle do under the influence of a magnetic field, as long as that charged particle is in its plasma form. And we're going to talk about some applications. Okay, how is this related to what we would like to study this semester? Okay, so just a brief recap or brief review of your forces on charged particle. So first is, if you have a charged particle creates its own magnetic field, electric field. Okay, so for a positive charge, okay, for a single positive charge, it creates an electric field that is pointing outward, radially outward by Coulomb's law. And on the other hand, if you have a negatively charged particle, that charged particle has an electric field around it or creates an electric field around it that is directed toward it. Electric fields are vector quantities. So it is described in terms of its magnitude called the electric field strength as well as a direction. So when we discuss or when we describe an electric field, it's very important to not only know the magnitude or how strong the magnetic field, the electric field is, but also just as important, the direction of that electric field. Now, if we have a dipole, an electric dipole for that matter, where we vectorially add the electric field created by this positive and negative charges, we create this electric field configuration of an electric dipole. So this electric configuration of a dipole generally tells us that the all electric fields emanate from the positive charge, and they uh, end up on the negative charge. Okay, just a few, notes about electric field. So the electric field configuration, we call this the electric field lines. Okay, so these electric field lines tell us the two things. Number one, the magnitude in that area or in that region, as well as the direction. So for example, if we're going to talk about this direction, this area has a weaker electric field because of this configuration wherein if the field lines uh, are less dense in a certain area in terms of number of lines per area, that means the electric field strength on that area is weak compared to regions wherein the electric field lines are closer to each other. And of course, you can see the direction. Okay, these are the direction of the electric field at certain regions in space. Now, how is it related to electric force on a charge? Because the electric force on a charge will also help or dictate how your charges move. Whether your charge is moving or not, it always creates an electric field. And it also behaves according to the influence of an electric field, whether the charge is moving or not. So by definition, the electric force on a charge is just the product of the charge itself that receives the electric force, F, times the electric field in that direction. So this equation is very simple, no? So that's a force is equal to the charge times the electric field. But this equation is actually very important because it tells you two things. Number one, it tells you how big or how large or strong the force exerted on this charge and the direction exerted on this charge. So for example, we have a positive charge here and we want to find the electric field at a certain point. Because this is a positive charge, the electric field points radially outward from your charge. So at this point, at point P, the electric field is directed in this direction. It's directed away from the away from the away from the charge. Now, if we place a charge Q on this point, what happens is that it will experience an electric force, F. The product of the magnitude of this force will just be the product of the magnitude of the electric field and the magnitude of the charge. Whether this charge is positive or negative, okay, the magnitude of the force will just be equal to the product of the charge and the magnitude of the electric field. Okay, now for the direction will be dictated by two things: the direction of the electric field at this point and the direction and the magnitude or the sign of your charge. Now, if this is if your charge here, Q, this is Q naught. Okay, so let me just write it here. This is Q naught. Okay, this is Q naught. So if Q naught is positive like this, okay, the direction of the electric force will follow the direction of the electric field. So that means in this case, the electric field points outward. That means the electric force points outward as well. Now, if we have a negative charge, the negative source charge, this is the source of your electric field at the same point. Because the source charge is negative, so that means the electric field is pointing in this direction. Okay? Now, if we have a test charge placed here, a positive test charge, the electric force will also point in this direction. Now, what happens if we have a negative charge? So for example, we have a point here, and so that means the electric field will be pointing in this direction. So this is your electric field. Now, what happens now if we have an a negative charge placed here? So if you place a negative charge here, negative Q naught, so because of the sign here, the electric force will be directed opposite the direction of the electric field. So in this case, the electric force will be directed in this direction. So this is very important. Why? Because in the space environment is a combination of your positively charged ions and the negatively charged electrons. Okay, so if those charged particles are subjected to an electric field, basically they experience electric forces that are opposite to each other. So if the charges will move to the left, if the positive charges will move to the left, the negative charges will move to the right. So there is what we call an opposing movement of charges. Okay, so that opposing movement of charges will actually dictate the current, some of the current systems in the space environment. Okay, now what about if we have a magnetic field? Okay, so we know that we first experience magnetic field when we're dealing with permanent magnets. So permanent magnets during your, high school or even your college classes, uh, that when you sprinkle iron filings around this magnetic field, around this permanent magnet will realign or will align these iron filings according to the direction of the magnetic field. So by looking at the pattern that the iron filings form, okay, we can actually deduce the magnetic field configuration around that magnetic permanent magnet. So for example, if you have a single bar magnet, it would look something like this, okay? And if we oppose the north and south poles of a bar magnet, it would look like this. So if we're going to draw the magnetic field configuration of these two sets of a permanent magnet, it would look something like this. Okay? So just like your electric field lines, the magnetic field lines will give you the direction of the magnetic field and the magnitude of the magnetic field at certain regions. Now, it's very important to note here is that, okay, you will notice here that this magnetic field configuration is for a bar magnet. And this is actually what generally how the magnetic field lines uh, will describe, or this is what the magnetic field lines for the Earth's magnetic field look like. Okay. Now, for this configuration, for a north against south configuration, you will notice that at this area, okay, the iron filings are basically aligned along a straight line. So if we're going to look at the magnetic field line configuration, but at the region between the north and south magnetic poles of our two bar magnets, you will notice that this will produce more or less parallel lines. Okay, and this is an example of what we call a uniform magnetic field. So this is called a uniform magnetic field from the term uniform. So that means constant. So that means within this region, we can safely approximate that the magnetic field between these two poles of this bar magnet are constant in magnitude, represented by equal spacing by the magnetic field lines, and same direction as seen by the arrows. So this is what a uniform magnetic field line looks like. Now, this is just one way to make magnetic field. Now, there's another way to produce magnetic field, and you already know this by by studying Faraday's law, wherein if you subject a wire or if you allow current to pass through a wire, that current, which is a representative or represents moving charges within that conductor, those moving charges actually creates its own magnetic field. So these are two examples of circular currents. So this is a singular ring current. Okay, take note of the term ring current. So this is a current that is in a closed loop. Now the magnetic field, you will notice that when you sprinkle iron filings around it, okay, as long as there is current flowing through this loop, this will create a magnetic field, and that is where, and that will dictate how the iron filings around it will be arranged. Now, if we make several ring currents or current loops closely together, we form a solenoid. And for a solenoid, the magnetic field configuration would look something like this. Or the iron filings will line up like this. Okay, just like this. Okay, so basically your solenoid is just a combination of closely packed circular loops. The configuration of the circular loop, the configuration of the magnetic field for a circular loop, given this direction of the current, is drawn like this. Whereas for a solenoid, it would look something like this. Now, it's very important to note here is that you will notice that when you have a solenoid, it basically produces the same or more or less the same magnetic field configuration as your bar magnet. Okay. Now, one important thing to note for a solenoid is that inside your solenoid, you will notice that the magnetic field lines are is uniform, just like inside between this north and south magnetic poles. So inside the solenoid, you have a uniform magnetic field configuration. Okay, so it's very important for us today to imagine what a uniform magnetic field line looks like so that we will appreciate more how or what non-uniform magnetic field lines looks like. Also, it is important to note that this drawings or this illustration only show you the two-dimensional magnetic field configuration. But in fact, in reality, the magnetic field is a three-dimensional field. Okay, but we can only draw in two dimensions, so that's why we only have these kinds of figures. Okay, so those are some of the important things to remember when we deal with electric and magnetic fields. Now, how do charges react to, for example, a magnetic field? Okay, when a magnetic field is present in a certain area, if you have a charge placed in that, for example, you have a you have a charge placed here. Say you have a charge placed here, say a negative charge. It doesn't automatically mean that this charge will react to this magnetic field. Okay, unlike when you have your electric force or electric field, as long as there is electric field, you place a charge in that electric field region, that charge will already react to that field. However, there is a second condition in order for a charge to react in a magnetic field, and that is the charge must be moving, and that motion should be transverse and not along the direction of the magnetic field. Mathematically, it's given by this equation. F equals Q times V cross B. Q is the charge, V is the velocity, so that means you have to know both the speed of your charge as well as the direction of your charge. B is the magnetic field vector, so that means we have to know the magnetic field strength and the direction of the magnetic field, okay, where your charge is located. Okay, so this is a cross product, so you can just review your cross product later on. But the point is that this equation tells us two things. It tells us that the magnitude of the force will just be equal to Q times the speed times the magnetic field strength times sine of the angle between the velocity vector and the magnetic field vector. So this is the magnitude of the magnetic force. Now, the direction of the magnetic force is given by your right-hand rule. And we're going to use the same right-hand rule via this cross product as we discuss some of the drift motion of your charged particles. Okay, so this is an illustration of how this equation tells you. Number one is, okay, again, v is the direction of the velocity. V is the velocity. So that means this is the speed and direction of this charged particle. This is the direction of the magnetic field. And by cross product, by right-hand rule, okay, again, you can just review your right-hand rule. The direction of the magnetic field, okay, will be in this direction. Okay. Now, as long as this charge Q is positive, okay, this will be the direction of the magnetic field. It is important to note here that because it's a cross product, the direction of the magnetic force is both perpendicular to V and B, to the velocity and the magnetic field. Okay? Now, if, so that means you will notice that this is a vector quantity. So whatever the sign of the charge is, that will also have an influence to the direction of the resulting magnetic force. So that means, for example, if we have this magnetic field line configuration, this is an example of a uniform magnetic field line. So this is an example of a uniform magnetic field line. Parallel magnetic field, just like what you saw earlier. Now, these two charges that is moving upward perpendicular to the magnetic field, they will experience the same force because they have the same magnitude, they have the same speed, they have the same charge magnitude, they have the same speed, and they are in the same magnetic field configuration, and the direction between their velocities and the magnetic field are the same. Therefore, the magnitude of the magnetic field would be the same, the magnitude of the magnetic force will be the same for both charges. However, the direction would be different. Okay, by right-hand rule, the magnetic field, the magnetic force exerted on the positive test charge or the positive charge here will be directed in this direction. Now, because this charge is negative of this charge, the magnetic force will point in opposite direction. So that means the object will have, these two particles will experience the same magnitude of the same magnetic force magnitude, but they will experience this magnitude or this force in different direction. Okay? Okay. Now, if we're going to look at the equation of motion of a particle under the influence of electric and magnetic fields, okay? So equation of motion is generally given by your Newton's second law of motion. So that is given by F equals ma. Force exerted on a particle is just equal to the mass of the particle times the acceleration of the particle that is caused by this net force. Now, because we're looking at the electric and magnetic field forces on your charge, this force will be expressed in this equation. So this is a combination of the electric force and the magnetic force. Sometimes we call this the Lorentz force. And this is equal to the mass of your particle times the derivative of the velocity with respect to time, which is your acceleration. Now, for simplicity's sake, let's set first that the electric field, let's say there is no electric field on a certain region, and that in that specific region. So that means the electric field is equal to 0. So that means the electric force is absent. Therefore, you'll just end up with this equation. M times the acceleration is equal to Q times the cross product between V and B. Okay, so this is the magnetic force, and this is the product of the mass and the acceleration. Now, how will a charged particle Q behave under this force? Now, let's consider, for example, a uniform magnetic field region. Okay, so this region of magnetic field is uniform because they all point into the page. So we're going to, by convention, we're going to use this symbol in order to demonstrate or to show that the magnetic field is perpendicular to this page and it's pointing towards your screen. So that's why it's called B in. Okay, so this is the region of the magnetic field. This is a uniform magnetic field. Now, let's say we have a charge here, and it is moving to the right with the velocity v. This charge has charge q. So we have q, v, and b. So we have q, v, and b. Okay? Okay. Now, by right-hand rule, the direction of the magnetic force exerted on this charge will be directed both perpendicular to the velocity vector and to the magnetic field vector. And by right-hand rule, it will be directed in this direction. Okay? So this magnetic force is exerted perpendicular to the direction of the velocity of your particle. And if we have that, if the velocity is moving to the right, and there is a perpendicular force exerted on it, okay, this perpendicular force will change the direction of this velocity. Therefore, it will experience an acceleration. Specifically, we call that acceleration the centripetal acceleration. And if we have a centripetal acceleration, okay, we now have a uniform circular motion. Okay, so we have a uniform circular motion, so that means this particle will move in a circle like this. And the direction of the magnetic force will always point towards the center of this path, of this circular path, defined by your r. We call r your radius. Okay, okay. And because of this, the direction of the velocity will always be perpendicular throughout this path. Okay, so this is how a positive test charge or a positive charge will behave under the influence of this magnetic field, under the influence of a uniform magnetic field. Okay, now just to summarize the slide. So again, if we have a magnetic field that is going in to this page, a positive test charge that is moving, okay, will move in this direction. So this is an example of a motion of an ion, okay, under the influence of a magnetic field. Because the electron is negative charge, is negative, therefore the force will be opposite. So therefore the direction of the what we call this the circular motion of a negatively charged particle, okay, will be opposite the direction of the ion. Now you will notice that the drawing shows that the ion will move in a bigger circle than in an electron. Okay. Now this circular motion, okay, have what we call a guiding center. And we call this the gyration of charged particle. And that guiding center is very important when we talk about drift. Okay. So several things that we can define using this discussion. Number one is what we call the gyro frequency or cyclotron frequency, omega. And that is equal to the magnitude of the charge, the magnetic field strength, divided by the mass of your particle. And the gyro radius, which is equal to the mass of that particle, the speed of that particle, divided by the charge of that particle and the magnetic field. Now, this gyro radius equation is very important because it tells us, number one, okay, the dependence of the radius of gyration to the mass, to the speed, even to the charge itself, as well as to the magnetic field. And we're going to use that relationships as we talk about drifts. Okay, so you will notice that if we have an ion, okay, ions are much heavier than your electrons. So that means the mass here would be higher for ion than electron. So that means the gyro radius of an ion will be bigger than the gyro radius of an electron, which is natural. Why? Because remember that this force, by Newton's law, tells us that this force will cause the object's motion to change. Newton's law tells us that the heavier the object, therefore it is harder for that force to change the direction in the form of acceleration. So because the ion here is heavier than an electron, so therefore it takes much effort to change the direction of the motion of this particle than for an electron. So it's easier to change the direction of an electron than an ion. Okay? So that's one way to look at it. Now, let's look deeper into the gyro motion. Now, from our example here, we first set that the magnetic field B is perpendicular to the velocity. Okay, so this is just a simplification just to demonstrate the gyro motion of an electron or a charged particle or an ion. Now, what happens if there is a velocity component where the velocity is not perpendicular to the magnetic field, meaning the magnetic field and the velocity is not at 90 degrees at each other. So that means the magnetic field and the velocity will have two components relative to the magnetic field. One would be parallel and one would be perpendicular. So if that's the case, okay, so if this is the charge and this is the velocity that is not perpendicular to the magnetic field, relative to the direction of the magnetic field, this velocity vector will have two components, a perpendicular component and a parallel component. So the net result is that the charge will experience two motions. Number one is it will experience a circular motion, just like this one. But because there is a parallel, there is a that because the magnetic field or that because the velocity of the particle has a parallel component along the direction of the magnetic field. So that means this charge will also move along the direction of the magnetic field. So the net result will be a spiral motion. So this spiral motion is evident for a magnetic field line configuration that is uniform. Okay, in a three-dimensional perspective, it would look something like this. Okay, so the motion of the particle, okay, will spiral like this. Okay, so this is the direction of your parallel magnetic field in a perspective mode, and this will be the direction of the charged particle. Okay, and this time the radius of gyration r will now be dictated by only the perpendicular component of the velocity. Okay, so what does it mean? It means that if, for example, the velocity moves along the direction, the velocity is parallel to the magnetic field. So that means there is no perpendicular component, or the velocity doesn't have a perpendicular component relative to the magnetic field. Okay, that means the charge will not have any gyro radius. So that means the charge will not gyrate. It will just move along the direction of the magnetic field line. Okay? Now, what if we have a non-uniform magnetic field? So let's say we have, for example, this magnetic field configuration. Okay? So in this region, the magnetic field lines are farther away from each other, and in this region, the magnetic field lines are closer to each other. Okay. Now, if you have a charged particle moving along this magnetic field line, what will happen is that it will gyrate and it will drift along the direction of your magnetic field line, like this. Okay, so the charged particle will move like this. However, there is a phenomenon called a magnetic mirror effect. That, for example, there is a certain angle, we call that the pitch angle, wherein at that certain angle, with respect to the magnetic field line, okay, this charged particle that is gyrating in this manner will actually will momentarily stop at a certain point here, and then after this point, it will bounce back like this. Okay, so here we have what we call a mirror point. Okay, so this is the iron orbit and reflection in a converging magnetic field. Now, if we have like a some sort of a bottle like a magnetic field configuration just like this, okay, wherein it at the left and at the right, the magnetic field is squeezed in, and then we have a weak magnetic field in between them. At certain directions of velocity, this charged particle will actually bounce in between this bottle, like this. Okay, and this is how we contain plasma. Okay, so in a plasma chamber, if you're going to search for the term plasma chamber, this is how it is done. So if you want to simulate, for example, uh, the uh, the space environment, where you're going to, let's say, we have a given plasma parameters, and you want to simulate a space environment in a plasma chamber. Okay, you do the plasma chamber will have a something like we have a configuration like this, because that will that this configuration will enable you, the user, to trap what we call plasma. Okay, and in this manner, if you want to, for example, you have a spacecraft or a satellite that you want to test for space environment testing, which is one of the standard tests when developing satellites. So you have to have a plasma chamber that we're going to simulate the simulate the electron density or the ion density in the space environment, specifically in the ionosphere where most satellites are parked or are orbiting. So if you know the typical electron density in the ionosphere, specifically in the F region, and you have a satellite that you're going to launch and orbit in that region, you have to test first that spacecraft in a simulated plasma field or plasma region. And one way to do that is by plasma chamber. Okay, so this is your bounce motion, and this is the second kind of motion that your particles experience in a magnetic field and electric field. Okay, so again, first you have your gyro motion, and then you have your bounce motion. Okay, now the third motion that we're going to talk about today is called the drift motion. Okay, so as you will notice here that on the upper right corner, I wrote the equation for your gyro radius. Okay, uh, earlier we talked about how charges move under the influence of a uniform magnetic field and an ununiform magnetic field. Now, what happens if we have an electric field configuration or contribution by an electric field? So if you have a charge like this, and the electric field and magnetic field are configured like this. So the electric field is pointing upward, okay, relative to your page, and the magnetic field is pointing toward you or away from the screen, perpendicular to the electric field. Okay, so again, the magnetic field and the electric field are perpendicular to each other. Just like in your, electromagnetic field or electromagnetic wave, diba? Wherein the magnetic field oscillates perpendicular to the direction of the oscillation of your electric field. Now, what happens here? Okay, so again, we now have we now have two charges, two sources of fields, an electric and magnetic field. Okay, so let me write the equation of motion here. So force will now be equal to Q. Now be equal to Q So again, you have your force. That is equal to Q times the electric field. So this represents your electric force, or the force exerted on the charge due to your electric field, plus V cross B. Okay, V is the direction of the velocity, and B is the direction of the velocity. Now, let's say that the velocity is directed in this direction, initially, at the start. So let's call this your initial velocity. Okay, so as I mentioned here, the direction of the force, initially the direction of the force, sorry. Okay. Oh, sorry. Okay. So again, we have the direction of the, let's say the direction of the force, the direction of velocity is in this direction. And then we can actually determine, so if this is the velocity, sorry, and this is the velocity, and let's say this is your charge Q, okay? So our force, we now have two kinds, we now have two kinds of forces, the electric force and the magnetic force. So the electric force will be directed in this direction, right? Because the direction of the electric field is in this direction. Now the magnetic force will now be along this direction. So V cross B would be in this direction. Let's call this magnetic force, Fm. Okay. Now, the effect, because we have two forces, so that means these two forces will have an effect on your charge. Okay. By Newton's second law of motion, force, which is equal to Q E plus V cross B, is equal to ma. So in this case, we have two acceleration. One due to the electric field, and the other one would be due to the magnetic field. So due to the electric field, this particle will accelerate in this direction. So there is a vertical acceleration. So the acceleration is in direction. So that means, it's called as A1. So that means along this direction, the object will speed up. Okay, so take note, the object will speed up in this direction. So that means as the object here moves up, the perpendicular velocity component increases. Okay? Now, this magnetic field will provide a perpendicular force. Let's call this A2 or AC. C means centripetal. So this acceleration is your circular acceleration. So as the object accelerates upward or speeds up upward, it will move in a circle. Now, because of the fact that this particle speeds up in this direction, so that means the gyro radius as it goes up will be bigger because of this relationship. So the effect would look like this. Okay, you follow? Now, at this point, okay, at this point, the velocity would be perpendicular to the electric field. Okay, so this will be the velocity. Okay, so at this moment, the electric field will be in this direction. The electric force would be in this direction, and the magnetic force will be in this direction. So that means this will start to move downward. Okay, like this one. Okay, now the velocity in this case will be downward. So the magnetic field would still be, the magnetic force will still be opposite the direction. But because this is a positive test charge, sorry about that. My physics is wrong. Okay, the electric force would always be upward because the electric field is always upward. Okay, so the effect here is that the net force on this particle will be zero here, so it will momentarily stop along this direction. But the velocity will always be moving perpendicular to this path. So it will continue to move in this direction until this point. Okay, so at this point, as I mentioned before, the velocity will be downward. The magnetic field will be perpendicular to the velocity, and the electric force will be upward. So that means while the velocity is in this direction, the electric force will be opposite to that. So this force will oppose the motion. Okay, physically, what it will do is this positive charge will slow down. So as this particle goes down, it slows down. Therefore, the radius or the gyro radius will be smaller as it goes down. And it would look like this. Okay, and at this point, the cycle will continue. Okay, so this is the drift motion of an ion under the influence of a magnetic field and an electric field perpendicular to the magnetic field. Okay, so you will notice that the motion of your particle will still gyrate, but the particle will actually drift to the right. That's why it's called drift motion. Okay, now for an electron, because of the negative charge, okay, it will move in this direction. Okay, now you will notice here that while the negative charge particle will gyrate in opposite direction compared to your positive charge, okay, their drift under this influence will be the same. Okay, so the particle drifts in a crossed electric and magnetic field that both ion and electron will drift in the same direction. And we call that your drift velocity. This drift velocity is different from the velocity here. Okay, this drift velocity is different from your drift velocity here. So we called it VE because we introduce your electric field together with your magnetic field. Okay, so again, we call this your drift velocity. Specifically, we call this velocity the drift of the guiding center. That's why I mentioned earlier the importance of the term guiding center. Okay, this velocity, V, is not the velocity of your particle. but the velocity of the guiding center. Okay, the center of your gyration. Okay, specifically, we call this kind of drift as E cross B drift with a general term or general expression as this one. Okay, we call this E cross B drift because when we take the cross product between E and B, we get the direction of your velocity. That's why it's called E cross B drift. So the velocity, the direction of the drift velocity will be determined or is determined by the cross product of E and B. So if we take the cross product E cross B, okay, we get this direction. So that's E cross B drift. Okay, this is important when we deal with plasma under the influence of both electric and magnetic field, as long as the electric and magnetic field are perpendicular to each other. And we will have an example or an illustration or an application of E cross B drift. Now, just to give you a further visualization, so I prepared here a video demonstration. In this case, okay, the direction of the magnetic field is into the page. You will notice in this direction, and the electric field is downward. The velocity is downward, and the charge is positive. Okay. Now, this is how the particle will. Sorry. Again. Okay, so that's how this charged particle will drift due to the influence of a crossed electric and magnetic field. So that is just one kind of drift motion that your particles or charged particle in the space environment do. Okay. Now, let's talk about another kind of drift motion. In this case, the field that is present is only magnetic field, but in this case, the magnetic field is not uniform anymore. So let's say we have a non-uniform magnetic field, wherein the magnetic field in this region is stronger than in this region. Okay, so in this case, the magnetic field is pointing toward you. It is stronger in this direction and weaker in this direction. Okay, so aside from the magnetic field that is going outward, there's another vector that is present here, and that is what we call the gradient magnetic field or gradient of the magnetic field. So the gradient of the magnetic field is a vector quantity that describes how the magnetic field changes in a certain direction. Now, in this case, the magnetic field uh, is stronger, becomes stronger as you go upward in the page. So the direction of the gradient B, that's why sometimes we call this the gradient B drift or gradient drift. The direction of the magnetic gradient B is upward. So instead of electric field upward, we have another vector, an influence. The magnetic field is upward. Okay, so what happens here now? So let's say we have an ion here. Okay, now the magnetic field in this area is stronger than the magnetic field here. If we're going to look at the gyro radius, okay, the relationship between the magnetic field strength and the gyro radius is inversely proportional. So that means the stronger the magnetic field, the shorter the gyro radius, the weaker the magnetic field, the larger the gyro radius. That's because the magnetic field for a stronger magnetic field, the magnetic force is stronger. So that means the magnetic force that causes a change in motion or change in direction of your ion or in your charge will be greater. So that means you will get a smaller gyro radius. So that means as the charge goes into a region of weaker magnetic field, the radius of gyration or the gyro radius is bigger. And then as you go, remember that this charge will still continue to move in a circle. It's just that the magnetic field strength will just vary in each region. Okay, so as the charge move in a circle, in the region of weaker magnetic field, the charge will circle around a certain gyro radius, gyros or guiding center with a larger gyro radius. And when it enters a region of stronger magnetic field, it will have or it will take a smaller gyro radius. And this will continue like this. Okay, in this case, the direction of the drift would be would be to the left. Now, what happens if we have an electron? Because of because of the dependence of the direction of the magnetic force on the sign of the charge, okay, the electron will move in opposite direction, so will gyrate in the opposite direction, and it will also drift in the opposite direction. Okay, now comparing your drift motion for E cross B drift, wherein regardless of the sign of the charge of your charge particle, the, the E cross B drift would still be in the same direction and with the same magnitude. So that means whether you have an ion, a heavy ion, positive ion, or a light electron, these two charges will still drift with the same drift velocity. So that means they will still drift in the same direction with the same speed. Whereas if the drift is due to a difference in the magnetic field region or in terms of strength, the direction of the ion drift or the drift of the ion would be the opposite the direction of the electron. And the speed of the drift will also be different. So again, the drift for an ion will be to the right, will be to the left, and the drift of the electron will be to the right. And the magnitude will be dictated by several things. The mass of your atom, the mass of your charged particle. So that means the heavier the mass, the faster the drift. The velocity, the initial velocity of your particle V, the magnetic field, the magnitude of the charge, as well as the magnitude of your magnetic. Okay, so this is now what we call the gradient drift. Okay, and this is very important when we have, for example, regions of different magnetic fields. For example, regions where the magnetic field of between two sources are interacting with each other. Let's say in the magnetopoles. Okay, we also have a drift motion due to the curvature of your magnetic field. Because remember that the Earth's magnetic field is curved. Okay, if you have this, if this is the Earth, this is the north and south pole, the magnetic field would look like this, right? So for the Earth, the magnetic field is actually curving like this. Okay. Now, because of the curve motion, remember that the gyro motion will still be there. But because of the curved magnetic field, there is an extra centrifugal force that is outward. And the net effect, I'm not going to the details of how this is done, but the point is that there is what we call a curvature drift. Now, what's important here is the direction of the drift, the curvature drift. The curvature drift will be dependent on the direction of your R. So this is the radius of curvature of your curving magnetic field and the direction of the magnetic field. So for example, if you have an ion here, okay, if you have an ion here, Okay. If you take the cross product of RC, that's the radius of curvature, and the magnetic field at this point, the magnetic field is in this direction. Okay, so R cross B, okay, R, so this is R cross B. The direction of the drift is in this direction. That is into the page. Now, therefore, if you have an ion, if you have an electron, it will move in the opposite direction. Okay, so this electron will move opposite the direction of your ion. Okay, so if we have a collection of particles, charged particle involving positive and negative charges, if we have a curved magnetic field, those two charges will move in opposite direction. They will separate. Okay, so that's your three drifts that is usually happening in the space environment. Okay, just to summarize, this is your E cross B drift. For an E cross B drift, both electron and ion will move in the same direction with the same drift velocity. For the gradient P drift, charges will move in opposite direction depending on the direction or depending on the charge and the direction of the gradient B. The curvature drift, this is the same. The charges will move in opposite direction. If the curving happens like this, so the direction of the magnetic field is like this, the positive ions will move in this direction, the ions will move in this direction. Okay, so this is the third motion of a particle in a magnetic field or a plasma particle in a magnetic field. Okay, so just to summarize the three types of motion, we call this the adiabatic invariance. We say adiabatic invariance, that means this gyro motion, bounce motion, and drift motion are actually happening slowly in an extremely slow time in a geomagnetic field. Okay, so again, there is gyro motion, there is bounce motion, and there is drift. Okay, now, so that means the overall motion of your particle, let's say starting at this point, the particle will move, will gyrate, and then will bounce, and it will drift in this direction. Okay, okay, if the magnetic field is in this direction, okay, if the magnetic field is in this direction, the curvature drift of this particle, if this is positive, okay, sorry, if this is the direction of the magnetic field, and the drift of this particle is in this direction, this particle should be positive. This should be positive. Okay, just like in your electromagnetic field, just like in your geomagnetic field. Okay, so for your geomagnetic field, again, there will be drift and there will be a mirroring. So the particle will gyrate along the direction of the magnetic field, but it will move bouncing off from the mirror points. Okay, and because the direction of the magnetic field is in this direction, ions will drift in this direction, and the electrons will move in the opposite direction. So the ions will move westward, the electron will move eastward. Okay, so this is what we call your eastward electric drift. Okay, and why is it important here? How is this important? So remember that the magnetic field configuration of the Earth is shaped like a donut like this. Okay, so we call this your flux tubes. And this trapped particle, this is the trajectory of your trapped particle, is precisely why we have trapped particles in these radiation fields. Call this the Van Allen belt because of this three invariant motion. So we have an electron belt, two electron belts, the outer electron belt, and the inner electron belt. And in between them, we have your proton belt. And this precisely because of the three invariant motions or three adiabatic invariants of your charged particle in the geomagnetic field. So you have your drift, your bounce, and your gyro motion. Okay? And because of the rotation of the magnetic field, because of this configuration, because there is a drift, eastward drift of your uh, westward drift of your of your protons, or let's say ions, positive ions, and you have your westward drift, your electrons. Okay, so if positive charges move westward, we actually call that the ring current. So this ring current is actually a result of that curvature drift of your protons or your positive ions in the space environment near the Earth. So that's one of the current systems present in the Earth's magnetosphere. Other currents, magnetopause current, field-aligned currents, neutral sheet current, tail current, and other kinds of current will actually depend on the three motions: charge, the three motions. So you have the electric field, the influence of the electric field, magnetic field, the drift, the bouncing motion, as well as your gyro motion. Okay, so this is your ring current. So ring current is very important for us because if, for example, this ring current, remember that current produces electric field, a magnetic field. So if this ring current is disturbed, okay, the magnetic field it produces will change that the magnetic field configuration of the Earth due to the interference or due to the influence of the interplanetary magnetic field, okay, carried by the solar wind. Okay, if the ring current is disturbed, okay, we have a geomagnetic storm. Okay, ring current is actually measured in terms of what we call your DST index, as well as your KP index. So these are indices that tells you if we have an ongoing geomagnetic storm. Okay, so this is just one application of single particle motion. In a more localized manner, in a more local setting, we also have what we call the equatorial ionization anomaly. In the ionosphere, the charges formed by solar radiation, by ionization of neutral atoms in the atmosphere that produces the ionosphere, while the while the sunlight that causes much of the ionization is concentrated in the equator. So we expect that there is just a single blob or single region of ionization in the equatorial region. However, okay, in reality, we don't have a single blob, but in fact, we have two large ionization crests. Okay, and on the on the geomagnetic equator, we have what we call a low ionization. So we have two ionization crests at the northern and southern geomagnetic latitude. Okay, and that is because of what we call the equatorial ionization anomaly. Okay, just to give you a perspective, okay, again, this figure shows the ionization globally at a certain time. Okay, so the more red the more red the region is, the higher the ionization. The bluer means the lower the ionization. Okay, so this tells us where, what time, what would be the local time in a certain region. Because remember that ionization is due to sunlight. So if you have low ionization, like in this direction or in this region, we now have, this is more or less, this is nighttime in this region, and in this region we have a daytime. Now in a different perspective, it looks like this. Okay. Now what happens here is that if you're going to slice the ionosphere in this manner or in this manner, it looks something like this. So the vertical axis is height, the horizontal axis is latitude, magnetic latitude, and the color means ionization. So just like here, we have two blobs of the equator. So if this is your equator, so this is the southern and northern crests. This region wherein this two crests is not too obvious, it might look like this. Okay, but if you notice that there is what we call a curving pattern here. This curving pattern is being follows the direction of the magnetic field. Okay, so all in all, this is what happens. As you earlier mentioned, in the equator, we have what we call the equatorial electrojet. So this is an electric field. Okay, so this is eastward electric field. So this is north, this is south. So into the page is eastward. So this is eastward. So we call this eastward electric field. Okay, and then on the equator, this is the equator, magnetic equator. The magnetic field is to the north, perpendicular to the electric field. Okay? Now, if we have an electric field perpendicular to the magnetic field, the plasma in this region, okay, will experience a drift, E cross B drift. So that E cross B drift will be upward. So what happens is that the ionization here in the E region will actually move upward. Okay, it will drift upward. Okay, it will drift upward. So that's your E cross B drift. It will drift this way and it will drift this way. Okay. Now, because this drift can only be so much, because you remember we have gravity forces and pressure forces, difference in pressure. Okay. So this particle will move. This ionization, these ions will move upward. Okay. But because of the gravity parallel to the magnetic field, this ionization will move here and here. So we call this the fountain effect. So the net effect is that this fountain effect will cause or will have ionization crest in the northern and southern part of the magnetic equator. And that is what we can see here, here, and here. Okay, so that's it. That's your single particle motion. And then if you're going to, if you're going to, this is just a simple, consequence of Lorentz force law. But again, if in reality, there will be times that the electric field, this equatorial electrojet will change, and even the magnetic field will change due to external forces. So that means, okay, the relationship between electric field and magnetic field that dictates the motion of your particles, that dictates the motion of your electrons and your ions in the space environment will now depend on the electrodynamics of those particles. Okay, that's why it's very important to remember your Maxwell's equations. Okay, so these Maxwell's equations together with your force law will give you a better understanding of how your plasma behaves as charged particles. Of course, it's a different story if you want to look at the collective behavior of your charged particle in a plasma. Okay, that's why usually we combine them to form magnetohydrodynamics. So we combine the electromagnetic behavior of plasma to the fluid behavior of plasma. So thereby we have a magnetohydrodynamic. Okay, and in the next week's class, that will be your task. I already prepared some lecture videos that you will uh, that you will do or that you will watch to better understand how uh, charged particle behave uh, as a collective element or as a collective species. Okay. There we're going to look into how charges behave as a fluid. Okay, so next week we will not meet anymore. Next week will be a synchronous class, and we will have your first online quiz after that asynchronous class. Okay? Questions, please. Questions, please. Ilan na nandito? 8 people. Questions po?
Sir, si Yvonne po may tanong.
May question po ako sa chat po.
Ano yun, Bon?
Sir, ask ko lang po paano po nalalaman kung hanggang saan po yung mirror point? Paano po siya na-define?
May tinatawag kasi sa mirror point, no? Okay, good question. Actually, skip ko na siya, but yung mirror point na tinatawag, hindi lahat ng particles in that kind of configuration will make a mirror motion, no? Meron siyang tinatawag na pitch angle. So depende yun sa sa angle that the particle depende dun sa particle sorry, ano ba yun? Hindi pala. Sorry. It will depend on ano ba? Okay. It will depend on yung angle dito. Angle of your velocity. So there will be hindi lahat trap. So hindi lahat trap. So depende sa ano. May tinatawag hindi ko na binanggit, no, because it might confuse pa, no. May tinatawag na loss cone. You just have to search this. Loss cone. So may tinatawag na pitch angle. So yung pitch angle yung itong angle na to. Okay, so for example, if the particle here, let's say a particle here moves in this direction, okay, because in this area, the magnetic field is in this direction. Ito yung magnetic field niya, di ba? Okay, so kung ang particle mo dito moves parallel to the magnetic field, it will not experience magnetic force anymore. So it will not gyrate. So it will just continue to move in this direction. Hindi siya magbabounce. Pero for example, dito naman yung direction, perpendicular naman. Okay, ang gagawin naman ng particle, it will just move in a circle. It will not move left and right. So depende yun dito sa angle na to. Natawag din pitch angle. But these are just special cases, yung makakawala yung particle. Ito, makakawala yung particle dito. Ito, makakawala yung particle.
Thank you, sir.
Ikaw, Ramon, may tanong ka, Ramon?
Wala po, sir.
Wala naman?
Pero ako po may question po. Doon po
Yes.
sa Van Allen belt something, yung dalawang belt, yung slide po na yun.
Okay.
Yung sa, ano tawag yun? Boundary po nung dalawa, yan po. Yung boundary nung dalawa
Ito.
na proton belt at saka yung electron belt. Hindi po ba may nangyayari doon? Ano po? Kasi di ba electron yung isa, tas proton yung isa.
Remember, yung
Hindi
electron
po
tsaka
nakikita.
proton are moving in opposite directions, no?
Opo, edi mas lalo pong magkakaparang eddy current.
Oh, kasama na yan. So it's a very complicated, no? It's a very complicated, electrodynamics there, no? Kaya kung mataas yung electron belt dito, maraming electrons dito kasi. Kaya ayan. These are very energetic electrons. Kaya tawag dito radiation to radiation. So if we say radiation, hindi siya electromagnetic radiation. These are particle radiation. Okay, that's why it's a no-no put satellites here because of that, strong presence of, electron radiation, which will cause damage to your satellites. So usually
Kunyari
either
po,
nandito siya sa proton belt or below sa yung inner electron belt. So hindi lahat ng places pwedeng lagyan ng satellite. Unless you want to measure Van Allen belt itself. So you have to put satellites in the Van Allen belt.
okay po.
Nakuha
Kunyari
ba ako? Yan.
Kunyari po meron pong outside na mga particles, kunyari po yung solar wind, ganun. Ano po epekto nun dyan?
Dito ito yung magnetic field, di ba? So pag may solar wind ka dito, usually perpendicular yung ang ma-affectuhan siya. Okay, once it disturbs yung the magnetosphere itself. So pag kunwari ito yung day side, kunwari dito yung araw. Tapos may solar wind dito. If this solar wind is pointy, the solar wind will carry your interplanetary magnetic field in a certain way that it compresses the side because of magnetic pressure. It may happen na this will, itong Van Allen belt na to will either move downward or move away. So for example, may nakapark ka rito nag-orbit ka rito na satellite. Tapos biglang nagkaroon ng radiation storm or nagkaroon ng solar storm. So this Van Allen belt is compressed in the day side. So this strong electron belt or outer electron belt might move near this satellite. So this satellite might be damaged or might be affected. So pwedeng ganun. So marami it's a whole semester of class just talking about Van Allen belts.
Thank you po.
Sir, just to clarify po, yung mirror point po kapag non-uniform magnetic field po.
Yes, yes. Itong mirror point na to will depend on the configuration of the magnetic field. Okay, so for example, if you have a plasma, let's say if you have a plasma chamber, the source of the magnetic field would look like this.
Okay po, sir. So, ano lang po, kapag non-uniform po, possible po ba na magkaroon ng uniform and non-uniform at the same time?
Sorry?
Uniform and non-uniform magnetic field po, possible po ba magsabay?
Hindi. It's either uniform or non-uniform.
Non-uniform, okay.
But maybe depende sa scale mo. If you're going to look at very small scale here, very small region, of course, in that region, uniform magnetic field. Otherwise, di siya uniform.
Thank you po.
May tanong si Agana. Sir, question, na electromagnetic lang po ba yung behavior ng ionosphere? May effect po ba ang neutral atmosphere? Meron din, meron din. Meron din, may effect din ng typhoon, may effect ng typhoon, ang earthquake, volcanic eruption sa, ano, ang tawag naman doon, mechanical effect, no? Mechanical effect sa, ano, so neutral wind, may ganon. So for example, okay, just to give you a, ano, for example, this one, okay, I will erase everything here. For example, yung ionization crest dito, meron kang ionization. Tapos magkaroon ka ng neutral wind that is equatorward. Neutral wind yan. This is a flux tube kasi. Your magnetic, your charges will only move along this direction. It will not move across. Okay, so pag magkaroon ng neutral wind, in this direction, equatorward neutral wind, what will happen is that this ionization will not move across the magnetic field. In fact, it will push up. It will push up the this ionization. So pwede, mechanical yon. But it doesn't, that mechanical effects must still, follow yung electromagnetic rules ng behavior ng plasma, as well as fluid. Remember, yung plasma is still a fluid. It is an ionized gas. So it also behaves as a fluid. Okay, it also behaves as a fluid. So kung ano yung rules ng fluid mechanics, fluid dynamics, it would still follow with the it will still follow it will be still followed by the plasma. Meron ng added effect, and that is the electromagnetic effect. So yung fluid mechanics tsaka electrodynamics ng plasma must go together. Kaya may tinatawag na MHD. Magneto hydrodynamics. So it's a combination of electromagnetism and hydrodynamics. And this is used to explain the collective behavior of plasma, including plasma in space. Again, this is just the tip of the iceberg, no? Doon sa mga hindi enrolled sa class ko, sa mga nag-sit in, if you want to know more about plasma, more detailed, a more detailed explanation of plasma physics, I would really, you can take a screenshot of this screen and then look at the playlist. No? So this will give you a more detailed explanation, especially yung mga plasma parameters, ano ibig sabihin ng, divalent, ano ibig sabihin ng number density ng plasma, ano ibig sabihin ng ion temperature or plasma temperature, ano ibig sabihin ng plasma density, pressure, etc. No? So it will be all discussed in this playlist, no? For next week. And this will and we will use those fundamental in fundamental especially say Ramon, no, for as we go along to this class, no, we're going to use those parameters. We have to be familiar to those parameters because those are the same parameters that we use to, let's say, describe solar wind. So if we're going to look at solar wind data, we're going to see, electron density, plasma density, ion density, even the magnetic field, proton density, makikita mo yan. So, pati yung temperature, plasma temperature ng solar wind. So, it's also measured by your, measuring spacecrafts like ACE and Discoverer satellites or spacecrafts. Okay? So by the way, just a few last notes, no, with this Maxwell equation, no. This is very important kasi this describes, what happens to the, for example, if there's a geomagnetic storm, okay, geomagnetic storm. So let's say if you have a geomagnetic storm, so that means there is the magnetic field varies with time. So this is not equal to 0. If this is not equal to 0 by Faraday's law, it will induce an electric field. So sometimes, meron tinatawag na geomagnetic induced current or GIC, which affects power lines and power plants. So if this is your geomagnetic field and it changes with time due to external forces like a solar storm, high speed solar wind, CME, if this change is strong enough, it will induce strong enough electric field in your power lines, and it will interfere to the electricity that flows through the power lines. So you call that geomagnetic induced current. And the primary electric field, the primary electric field, the primary electric field, natural electric field that is affected is this equatorial electrojet. So that's why this is very important. So this equatorial electrojet is very important for GIC. And as you will notice here, the Philippines is in that region.
Sir, may
Okay.
tanong din po pala akong tungkol doon. Doon sa slide na yun. Yung slide po before. Sakto po na yung doon sa may part ng Pacific, wala talaga nung yan.
Sorry?
May epekto po ba yun? Kasi na-observe ko lang po yun doon sa Pacific part.
This one? You're talking about this one, Christian?
Apo, wala pong, ano po yun? Electron.
Isabihin na nighttime lang. Pag nighttime, walang source ng ionization, walang energy na mag-aayos na atmosphere, so mababa ionization. Ito, daytime.
Okay.
Ito yung nakaharap sa araw. Yan lang yan. So as time progresses, this region of ionization will actually move to a place where the Earth is facing the sun, or yung Earth, yung tinatawag namin na day. So ito yung tinatawag na day side. Ito yung tinatawag na night side.
Okay po.
Question po, sir.
Yes, Ramon.
Sir, di ba since mataas yung ionization dito sa day side natin compare sa nasa
Night side?
nasa north and south hemisphere?
Okay. Ano tanong mo doon?
Hindi ba practical na maglagay ng satellite sa atin? Kasi since yung 'di ba microwave transmission yung ginagamit natin. Mag-aayos.
Yes, actually
Since mataas yung ionization niya.
That's true, no. That's why that's why it's, for example, for communication, for GPS. Okay, the United States have invested a lot of money in, looking at they launched that CNOPS, the satellite. So CNOPS satellite is actually a satellite system that focused on studying equatorial ionosphere, because they appreciate, or they recognize the fact that a lot of things are actually happening in the equatorial region. And this is very important for them kasi for military purposes. So for example, say most of their activities sa military is in the equator. So mayroon silang may mga base sila sa equator, along Hawaii, Guam, di ba? In South China Sea, in the Atlantic Ocean, in the Indian Ocean, marami silang dyan. So, and even their aircrafts, which are highly dependent on GPS, and even with their their missiles, no? So aside from the fact na malaki talagang ionization in the equatorial region, ano pa, susceptible din to for irregularities. So imagine magkaroon ka ng bubble, plasma bubble dyan. Okay, so that will affect radio propagation in the equatorial region. That's why it's very important to in the Philippines, for example, we are in a very special region of the space environment kasi we are actually the whole country actually belongs to the equatorial region as well as in the low latitude region. Ganun din naman ganun din naman ang Africa and India. Pero yung sector natin is different from their sector. Iba yung behavior. Mas remember yung configuration ng geomagnetic equator would look something like this. Okay, so pag iba yung geomagnetic equator, iba rin yung magiging behavior ng ionosphere. So baga iba yung behavior sa atin, iba yung behavior sa Indian region, iba rin yung behavior sa African region, iba rin ang behavior sa South America region.
Okay po, sir. Thank you.
Swerte ngayon lang kasi for the past few years, no, swerte talaga lang ng Pilipinas kasi hindi pa ito nararanasan masyado ng Pilipinas. Yeah, so in relation to Diwata 1 and Diwata 2. Kaya mahaba rin ang buhay ni Diwata 1 tsaka ni Diwata 2 kasi we are in the current solar minimum. So this ionization is not really too violent or too variable. Mababa ionization and the occurrence of such irregularities in the ionization crests is not that often. Although one of my students is actually studying that, no. But as we start the new solar cycle 25, okay, there's no way but the solar activity will start to increase again. In 5 years, maybe 6 years, we will reach solar maximum. And then that is the time where in relation to satellite park in the low Earth orbit, even in the high Earth orbit, okay, they are more susceptible to space weather effects. And even your GPS navigation or GNSS navigation will be highly affected. Aircrafts might be affected kasi yung kanilang mga mga autopilot nila are usually guided by positioning by navigation systems. So if there's something happens in the equatorial region, even in the polar region, kung malakas ang aurora, talagang malaki yung effect sa aviation. Not to mention yung effect niya sa equatorial electrojet, which will might induce GICs. Okay ba? Exciting? Questions po? Sayang wala si Eliza. Anyway, okay lang naman. Questions po? Anyone? Ramon, may tanong
Sir,
ka pa,
may tanong
Ramon?
po sa Ate Agana sa chat.
May tanong sa Ate
Sa chat
Agana
po.
sa chat. Okay. Nagtanong pala kanina si Merlin pala yung nagtanong kanina. Sorry, Merlin. Okay, Agana, tanong ni Agana. Dito lang po ako mag-ask. What are the requirements po para masabing okay maglagay ng satellite sa isang location po ng space? Well, actually lang talagang iniiwasan talaga would be yung Van Allen belt. Talaga. Ito talaga isa sa mga pinaka-iniiwasan. Unless you want to study the Van Allen belt, no? But for other purposes, you cannot really park here kasi talagang malaki talaga ang radiation dito particle radiation dito sa Van Allen belt. So usually dito, sa mababa yung ionization. So in between this this belts, no. So yeah, yun yung mga, and even in the in the low Earth orbit. And also as other than that, no, the altitude that you are going to park your satellite will also depend on the kind of application that you want. Or if you want to look at one region in space 24/7, you have to place your orbit way above the way above the Earth's altitude, no. Because you have to, remember, 'di ba sa physics, 'di ba? Yung orbital velocity niya ng satellite will depend on the how far you are from the Earth. Diba? So kung gusto mong sabayan yung Earth, so that will also determine kung gaano kataas yung So depende din sa period so if you're going to look at your simple orbit equations sa physics mechanics natin before, you will notice that yung radius of circular motion of your satellite will depend on the period as well. Or the period will depend on the radius now. So kung ano yung requirement mo na period, that will determine primarily kung saan mo siya ilalagay in orbit, no. So ganun. So depende talaga sa ano yung use, and then but primarily iwasan mo talaga itong mga radiation belts na to. Primarily.
Sir, may spacing po ba yung satellites dun sa pag nilalagay po nila?
May spacing din sila, no. So kasi yung spacing na importante yan for to avoid collision. All the satellites in orbit are still few compared to the kumbaga yung yung density of number of satellites per orbit, no, per height. But meron kasi merong national, may international organization that handles kung saan mo pwedeng i-park. Hindi ka pwedeng basta-basta kung saan lang nagpa-park ng satellite. Because isa sa ina-avoid would be collisions between satellites. Because remember, 'di ba, sa mahina ang gravity sa low Earth orbit, even sa high Earth orbit. So wala masyadong air resistance. So once you start your object moving, once an object starts moving by Newton's first law, it will continue to move. And if there is an extra force there is a net force. That force will accelerate your particle. So the or your satellite will speed up as much as it can. So kung super bilis na nung satellite, kasi kumari na pawara yung satellite or mali yung pagkakapark, so that satellite might hit something that can be very destructive din sa ibang satellites, no? Sabi daw ni Merlin, meron na raw 18,000 objects na recorded na nasa space objects, no? Okay. Merlin, kasama na ba dito yung mga junk, mga decommissioned satellites na nagpo-float lang? Okay, hindi ko alam masyado yung in terms of the numbers na. But this 18,000 will still be kulang malit pa rin to, no? Malit pa rin to. So yung chance, I think for personally, no, the chance of bumping between satellites is not it's not that it's not that high compared sa probability, for example, na magbangga ng mga eroplano sa Pilipinas, sa mundo. Ayan, pati daw debris. Punta tayo sa satellite, no? Gusto kong iwasan yun, no? Importante sa akin yung space plasma, no? Questions po? Questions po? Wala na?